Hi all, let's take a look at the problems here in section 7.5 dealing with partial fraction integration. This is one of my absolute favorite sections of the semester. We can actually make these partial fraction integration problems as difficult as we would like. There are some problems that I could give you like this that would take multiple pages to work one problem. There's only one problem that's what I would consider remotely difficult in this assignment, and that's the gorgeous number 11. But there could be much worse problems than that. But that's as hard as we will get. Let's go ahead and start talking about the algebraic basis behind partial fraction integration. So this first problem just has us set up the partial fractions that would then be easier to integrate. So it gives you the function f of x is equal to negative 10x squared minus 4x minus 72 divided by the irreducible quadratic x squared plus 25 times the linear factor x plus 1. Well, what you're supposed to remember when we try to reduce this fraction down into its two separate components, and you say, well, how many different fractions do I need? Well, you need as many fractions as you have factors in the denominator. I will need two separate fractions here. That first factor in the denominator is an irreducible quadratic. You cannot factor x squared plus 25 any further. So anytime the denominator is of quadratic power, your numerator needs to be of linear power. So I set it up as ax plus b over x squared plus 25, a generic linear function. You think of it as a linear function mx plus b, but now you want to call it a and b so you can orderly find your constants that you need. We always go a, b, c, d, e, f, g, however many we need. In this case, I have ax plus b over x squared plus 25. Now, plus the constant factor c over the linear factor x plus 1. We have to understand to break it up like that. Now, in order to solve for a, b, and c, all that we have to do is multiply by the least common denominator on both sides. When I multiply by that least common denominator on the left, of course, I get the numerator. When I multiply by it on the right, I get the group ax plus b times x plus 1, and then c times the group x squared plus 25. That allows me to solve out for each of these letters, A, B, and C, that I don't know. First thing I do is I think, well, as long as I could set one of these factors equal to 0, I know I'm going to be able to solve for a variable. Well, you can't set the factor x squared plus 25 equal to 0, but I can set the second one equal to 0. X plus 1 is equal to 0 when x is equal to negative 1. I let x equal negative 1 on the left-hand side, and I would get negative 10 plus 4 minus 72. That ended up giving me negative 78. Now, plug a negative 1 into the right-hand side, and you can see the a and the b cancel out because they'll be multiplied by a group that's equal to 0. C, when you plug in a negative 1, is going to be multiplied by 1 plus 25, which is 26. We get 26c is negative 78, divide by 26 on both sides. You can see that c is negative 3. All right, now I have my answer for c. I can use that to then help find a. And the reason that I can logically solve for a now is because once I know c, I already know that the coefficient, and notice how I start this and try to show my work by asking you, consider the x squareds. Well, please look, on the left-hand side, the coefficient of x squared is negative 10. So I know any coefficients of x squared on the right-hand side also have to add to be negative 10. So I say negative 10 is equal to, what are the coefficients of x squared on the right-hand side? B is not a coefficient of x squared, but I can see that both a is going to be a coefficient of x squared and c is a coefficient of x squared. So I can say, well, then I know a plus c has to equal the coefficient of x squared on the left, which is negative 10. I already know c is negative 3, so I would get a plus a negative 3, or a minus 3 is negative 10. Thus, a is going to be negative 10 plus 3. A is negative 7. Now that you know what a is, you can look at the constant in this expression. You already know if you look at the constant in the expression, well, the constant on the left-hand side is a negative 72. Now, how could you get a term that's not a variable coefficient on the right-hand side, just a constant? Please notice A can never be a constant on the right-hand side because it's tied with the x, so it's always a coefficient of x squared or x. Well, what about B? B is a coefficient of x, and B is also a constant, plus 1b. So I can say, well, I can have a constant of B on the right-hand side, plus I know that 25c would be a constant. So then I can say B plus 25c is equal to negative 72. I have already solved for c as negative 3, so 25 times negative 3 is minus 75. B minus 75 is negative 72. Add 75 to both sides, you'll be able to see that B is equal to 3. Now that you've solved for A, B, and C, you can rewrite your partial fractions and say, all right, my original function f of x is equal to ax plus b. Well, that's negative 7x plus 3, all divided by x squared plus 25. And then normally I would say plus c, where c is negative 3, so plus a negative 3 over x plus 1. I went ahead and wrote it as minus 3 over x plus 1, same thing as plus a negative. And I could easily see that on my answer choices that was equal to the second choice. For the next question here, they give us a similar problem, and they go ahead and solve for what A and C are in this problem and ask you to solve for B. I really didn't like that. I wanted to go ahead and do the full-fledged work of the problem, so that's what I did. I went ahead and wrote the expression that they gave you there, or the function 3x squared plus 25x plus 33, all divided by x plus 8 times x plus 3 squared. Okay, now I know that when I deal with this, and I'll make this a little bit bigger here. When I deal with this, I can say, well, I look at those denominators, the x plus 8 and the x plus 3 squared, and I can say, well, for any linear denominator, it's going to have a constant numerator, so a over the factor x plus 8. Now I look at the second factor, and I need to understand that is not a quadratic factor. That is a repeated linear factor. It's the linear factor x plus 3 that just happens to occur twice. So you say, well, all right, then for every power of that linear factor, you're going to need a different constant numerator. So I put plus b over x plus 3 to the first, plus c over x plus 3 squared. Now, the number of letters that you're going to need to solve for is always the same as whatever the degree of the denominator is. I look at this denominator and say, well, it's going to be degree 3. I knew I would need an A, a B, and a C. If it were degree 4, I would need an A, B, C, and a D. Now, in order to simplify for these partial fractions, I go ahead and I multiply by the least common denominator on both sides. The left-hand side, I get my numerator left over. The right-hand side, I'll have A times x plus 3 squared. Then I'll have B. B is going to be multiplied by one factor of x plus 3 and the x plus 8. The C is only going to be multiplied by x plus 8 because the x plus 3 quantity squared would cancel with its denominator. Now, in solving for A, B, and C, I can set these denominators equal to 0. I can say, well, I know I could solve for, now I solve for B first. I could solve for B, or I should say C, if I let x equal negative 3. All right, so as long as you set each of your denominators equal to 0, you'll be able to solve for a variable. I know I can solve for a variable if I let x equal negative 3, and I know I can solve for a variable if I let x equal negative 8. Please notice that's the two values I let x equal. When you allow x equal negative 3, plug a negative 3 into that polynomial, you'll get a negative 15. Plug a negative 3 into the right-hand side, the a gets multiplied by 0, the b gets multiplied by 0. You'll only have c times negative 3 plus 8. We know that that's going to be 5c is negative 15. Thus, I can say that c is going to equal negative 3. Now that I've solved for c, I can go in and solve for a if I let x equal negative 8. All right. x equal -8 on the left-hand side. When I plugged that into that polynomial on the left, I got a positive 25. I plug a -8 into the right-hand side, and I know that the b and the c terms would cancel because they'd be multiplied by 0. The a term is going to be multiplied by -8 plus 3 squared. Well, we know that that's 5 squared, which is 25. So then I can say, well, then 25a is going to equal 25, which then tells me a is equal to 1. Now, I have my solution for c and my solution for a. I have to use a little bit more creativity to solve for the remaining variable b. So what I did is I went to the original expression that I have up here after I got rid of the denominators, and I recognized a is going to be a coefficient of an x squared, b is going to be a coefficient of an x squared, c is not going to be a coefficient of an x squared. So I said, let's consider the coefficients of x squared. The coefficient of x squared on the left-hand side is 3. We know the coefficients that will sum to be the coefficient of x squared on the right-hand side are going to be a plus b. So a plus b has to equal 3. Now, I already know that a is 1, so I get 1 plus b is 3. Well, then b is 3 minus 1. B is 2. So now I have my answer for a, b, and c. And then in order to get that for the answer on achieve, I had to, because I first, you'll notice on mine here, it says it took me 2 attempts. Well, that's just because the answer for B is really 2, but they're specifically saying let's subtract that second fraction with the B in the numerator. So if you need that numerator to be a positive 2 and you have a minus out in front of it, then B is going to have to be a negative 2. So that's what I put in red over here. I had to input B equals -2 since achieve very sillily, that's not even a word, but unfortunately, achieve had the minus in front of the second fraction, which forced me to change the sign of that to get the -2 to fit what they were doing. Okay, up next here. Good question. For number 3, we have the integral of x with respect to x over 13x minus 12. So I just have that one linear factor in the denominator to the first power, but my numerator is to the first power as well. What you're supposed to remember is anytime the denominator and the numerator are of the same power, or even if the numerator is of greater power, your first step is divide that denominator into the numerator and simplify. You must do the algebra before you do the calculus. The only way we could just go straight forward and start the integration process is if the denominator is of greater power. So I had to divide the 13x minus 12 into x. I showed that over here with long division. There's really not a lot of work to show, but I could see how some could get confused here. You say, I need to divide 13x into x. Well, it'll go 1/13 of a time. 1/13 times 13x gives me x. 1/13 times a minus 12 will give me minus 12 over 13. But now you need to remember we always subtract that group out. Well, that's why the x minus x cancels. But then you'll have minus a -12 over 13 gives you positive 12 over 13. Now, that's my remainder. The whole point of a remainder is that it remains divided by the denominator. So I can say, all right, this original integral is the integral of this part divided out evenly. So it's just the integral of 1/13 with respect to x. Now I'll say the part that remained is going to remain divided by this denominator. Instead of leaving it in the numerator of this separate integral, I went ahead and factored it out. And I can say, well, that's the same thing as the integral of 12 over 13 divided by 13x minus 12. So now this is a better format. And what I can remember is that anytime I have the derivative of a function divided by a function, it's going to be the natural log of the denominator. Please think about this. And I'm doing it without a formal u substitution, and I would like you to be able to as well. If you did a u substitution here, you'd say, well, what if I let u equal 13x minus 12? Well, then du would be 13x dx. Notice that's what I've put in this step. I've multiplied the inside by 13. I've divided by 13 on the outside. Now, what would this give me? It would give me 1 over u du. Well, you know that the integral of 1 over u du is the natural log of the absolute value of u. That's what I'm doing from here to here without formally using the u substitution. Once you start getting more and more comfortable with substitution, especially a simple u substitution like where u is just the denominator, we typically don't show it. Now, if you want to show it, you're certainly welcome to. But it's better if you get out of it and show your work like I'm doing here. So now, anytime the derivative of the denominator is over the denominator, so derivative of 13x minus 12 is 13, well, then that's going to be the natural log of the absolute value of the denominator, done, plus c. And you'll notice that the answer I have here is the answer that I entered in and achieved, and it worked out just fine. For the next question here, we have, here's my work for it. Yeah. And we have the integral of dx over x minus 15, x minus 24. This is going to be the simplistic case 1 scenario where your denominator is a product of linear factors. That's really the easiest type case. So what I went ahead and did is let's do the algebraic simplification first and say, well, we can't deal with it as it is. So we're going to call this a over the linear factor x minus 15 plus b over the linear factor x minus 24. I then simplify by just saying, let's multiply by that least common denominator, x minus 15, x minus 24 on both sides. When you do that on the left, you just get the numerator 1. On the right, you'll get a times the other denominator, x minus 24, and then you'll get b times the other denominator, x minus 15, since the x minus 24 would cancel out in that second term. Now, when I'm looking at this expression, I can then say, well, I should be able to solve for a if I let x equal 15. When I do, the left-hand side doesn't care if x is 15, it's just a constant of 1. On the right, the b would cancel out because it would be multiplied by 0. The a is going to be multiplied by 15 minus 24, or negative 9. So I get negative 9a is 1, thus a is negative 1/9. Now, if I solve for b, I need to let x equal 24. Again, the left-hand side, it's still 1. The right-hand side is going to equal b times 24 minus 15. That gives me 9b is 1, thus b is 1/9. Now, I have my answer for a and I have my answer for b. They're just the opposites of one another. So then I can go back to my original integral. This original integral is equal to a over x minus 15. So instead of putting the negative 1/9 in the numerator, I preferred to just factor it out and say, well, it's 1 over x minus 15 with respect to x. Every single solitary time, if the derivative of the denominator is in the numerator, your answer is the natural log of that denominator. So you'll see I just put negative 1/9, natural log of the absolute value of x minus 15. Similarly, for the second one, that b could be factored out as 1/9 times the integral of 1 over x minus 24, and that would integrate to be 1/9 the natural log of x minus 24. And again, that's because the derivative of the denominator would be 1 with respect to x. So if you did a u substitution, this would simplify to be 1 over u du, which is the natural log of the absolute value of u. Now, when I did this problem, you'll notice, again, it took me 2 attempts. The thing that I forgot in this one is I didn't put the absolute values in my first attempt for the problem, but what I did there is precisely what they need. So notice here, if I show you my first attempt that they didn't like, I lacked the absolute value. So it would have been the correct answer, of course, if I put the absolute values, but I didn't, thus it wasn't. They will require you to do that. Number 5 here, it's a good question. We have the integral of the quadratic x squared plus 3x minus 39 integrated with respect to x over the linear factors x plus 3, x plus 8, 8x minus 3. I already know that this one is in the format where I can just go ahead and start partial fraction integration because the numerator is of lower degree than my denominator. My numerator is degree 2, my denominator is degree 3. So I go ahead and I set up my fraction to where I'm going to create partial fractions over each of those linear factors in the denominator. I need a constant numerator. Now I'm trying to solve out for a, b, and c, so I multiply by that least common denominator on both sides. When I do, your a is going to be multiplied by the other two denominators, x plus 8 and 8x minus 3. Your b is going to be multiplied by the denominators of the other two, x plus 3 and 8x minus 3. Your c is going to be multiplied by these two denominators, x plus 3 and x plus 8. Now, in order to solve for a, you should let the term in its denominator equal 0. You say, well, I can solve for a if I let x equal negative 3. I do that. Plug negative 3 into this polynomial on the left, you'll get a negative 39. Plug negative 3 into the right-hand side, b is going to be multiplied by 0, c is going to be multiplied by 0, a is going to be multiplied by negative 3 plus 8, which is 5, and 8 times negative 3, negative 24 minus 3 is negative 27. So I get a times negative 135 is going to equal negative 39. So a is negative 39 over a negative 135. That's going to reduce down to a positive 13 over 45. Reduced down by a factor of 3 over 3, and the negatives cancel. Now, when I let x equal negative 8, it should allow me to solve for b. All right, when I did that on the left-hand side, I had a positive 1. When I plugged the negative 8 into the right-hand side, a is multiplied by 0, c is multiplied by 0. The b is going to be multiplied by negative 5 times, this would be negative 64 minus 3, which is negative 67. So now negative 5 times negative 67, that gave me a positive 335. So I can say, well, b is equal to 1 over that 335. And then finally, a little trickier, but not a big deal, if you set this denominator equal to 0, you get 8x is equal to 3, so x is equal to 3 over 8. If you allow x to equal 3 over 8, it should enable you to solve for c. So I left that as a fraction, 3/8, plugged it carefully into the left-hand side to get the fraction negative 2,415 over 64. And then I can say, well, I know that a is going to be multiplied by 0. 8 times 3 over 8 minus 3 is 0. Same thing here. B is going to be multiplied by 0, so they cancel out. On the right-hand side, I would have, when I plug a 3 over 8 into this expression, you'd have 3 over 8 plus 24 over 8. That's where the 27 over 8 came from. Here you'd have 3 over 8 plus 64 over 8 for the 67 over 8. So then I went ahead and took the reciprocal of those two fractions. I said c is going to equal negative 2,415 over 64 times 8 over 67 times 8 over 27. And that simplified down to the fraction, I use my calculator, of course, negative 805 over 63. So now I have a, b, and c solved for. I just go back into my integral and say, well, all right, the original integral is equal to your first term. Well, you're going to have, let me bring this up a little bit more to show it. Your first term here, instead of a, which is 13 over 45, I factored that outside the group and said, well, then it's just going to be 1 over x plus 3 integrated with respect to x. I see the derivative of the denominator in the numerator. That's just going to be 13 over 45 natural log the absolute value of x plus 3. The next term, well, it's going to be the integral of b over x plus 8, where b is this 1 over 335. Again, notice I went ahead and factored that out. 1 over x plus 8, derivative of the denominator is in the numerator. So I can say that's going to be 1 over 335, natural log of the absolute value of that denominator. Then my last term, it was not as simple, had to be careful here. So again, I know that this would have been plus C, which is a negative 805 over 63, and then I would have the over 8x minus 3 integrated with respect to x. Okay, I knew that that term wasn't helpful on the inside, so I went ahead and factored it to the outside. I put plus the negative 805 over 63. And now I know if the inside is to be a natural log of the absolute value of the denominator, I need to see the derivative of that denominator in the numerator. So in this step, I went ahead and I said, well, let's just go ahead and multiply the numerator by 8. That 8 was not previously there. So I had to make up for that by dividing by 8 on the outside. Notice division of 8, multiplication of 8, they would eliminate. So you can say, okay, then all is fine. Now, the inside, you're going to have the natural log of the 8x minus 3, since, or natural log of the absolute value of 8x minus 3, since the derivative of the denominator is in the numerator. The outside, I just multiply these two, and I'll get the minus 805 over 4824 times that natural log. And then you input all of those values, and you see that Achieve liked it. It liked it a lot. The next question here, and this one comes with a warning. I didn't delete it from the work that I have scanned and posted online because what I did was a beautiful problem. But my number 6 that I first did is not correct with Achieve. Why not? Well, because I typed, or I didn't type, I wrote the problem down wrong. My denominator was supposed to be x minus 1 times x plus 1 squared. But doing it in this fashion, it created a perfectly nice problem. I really enjoyed working it, but I worked the wrong problem. So that's why I put this problem is correct. I didn't want you to think I made a mistake. I didn't. Well, I guess I did, copied down the problem wrong. So the problem we need to be looking at is this one. And what it entails is a very similar problem. We have the integral of 17x squared plus 26x plus 5 divided by x minus 1 and x plus 1 quantities squared. All right, so I algebraically simplified that by just saying over every linear factor, I need a constant numerator. In this repeated linear factor, it will need 2 separate numerators, 1 over each power of that linear denominator. Now, I can say, all right, we'll multiply by the least common denominator on both sides. When you do, the left-hand side is just the numerator. The right-hand side, you're going to have a, the x minus 1 would cancel, but you'll have a times x plus 1 quantity squared. You'll have b times 1 factor of x plus 1 and the factor of x minus 1. So I say times x minus 1, x plus 1. The c is going to not have the x plus 1 term because it would cancel out with its denominator, but it'll have 1 factor of the x minus 1. Now I can say, okay, I have that simplified out. I should be able to solve for my variables. Well, how do I solve for a? Well, I solve for a by setting x equal to 1, since that would cause its denominator to be 0 here. So if I let x equal 1, then please notice b is going to end up being multiplied by 0, c is going to end up being multiplied by 0. If I plug a 1 into the left-hand side, I just get 17 plus 26, which is 43, plus 5 is 48. On the right-hand side, you have a times the group 1 plus 1 squared, so that's a times 2 squared. 2 squared is 4, so you get 4a is 48. A equals 48 divided by 4. A is 12. So now, if I want to solve for the another variable, and it's not actually going to solve for b, it's going to solve for c, I can solve for c by setting x equal to -1. And so if I set x equal to -1 and plug that into the left-hand side, I promise you get a -4. On the right-hand side, the a is going to be multiplied by 0. The b would be multiplied by a factor of 0. The c is going to be multiplied by a factor of -2. So I get negative 2c is negative 4. Thus, I can see that the answer for C is 2. Now, I have the answer for A. I have the answer for C. This is where students usually fall into some trouble. They're like, well, I can't solve for all of the variables. Of course you can. You have to use a little bit of creativity now. What I can see is that A is a coefficient of x squared in this problem. B is a coefficient of x squared in the problem. So I ask you to look at the coefficients of x squared. On your left-hand side, well, the coefficient of x squared is 17. The only coefficients of x squared on the right-hand side, notice C is not a coefficient of x squared, but I would have A plus B are coefficients of x squared. I already know A is 12, so I get 12 plus B is 17, thus B is 5. Now, once I know that, I can go in and say, well, then my original integral in this problem is equal to A, which is 12, I'll factor that out, over the integral dx over x minus 1, plus B, which is 5, I'll go ahead and factor that out over the integral dx over x plus 1. Remember, we're integrating each of these since the original fraction that we're breaking up was integrated. And then my last one, need to be more careful with this one. This one is not going to be a natural log because that group is not to the first power in the denominator. So the C, which is 2, you'll notice I went ahead and factored that 2 out. But then instead of calling that 1 over x plus 1 squared, I said, well, that'll be more easy to integrate if I call that the group x plus 1 to the negative 2 power. And then I can say, all right, how do I integrate? Every single time, if the derivative of the denominator is in the numerator, it's the natural log of the absolute value of the denominator. So you see the first two terms integrate ridiculously easy. The third term, not bad. You can say, well, it's going to be 2 times the group. You've got to remember, if you have a linear function to a power, you can just say, well, all right, this is the reverse chain rule. In chain rule, I would bring the power down, then in front multiply, and then decrease the exponent by 1. When I integrate, I can say, well, it's this group to the 1 higher power divided by that new power. So I get x plus 1 to the negative 1 divided by negative 1 plus our constant of integration. Now, this is sloppy here. I would never leave it like that. What you're supposed to understand is that, well, this 2 divided by negative 1, that's just going to make that a minus 2. And this x plus 1 to the negative 1 power means it's dividing that 2. It's going to be in the denominator to the to the first power. So it's x plus 1 to the first in the denominator. And then, of course, plus our constant of integration. Now, you can see that's exactly how I entered that one in to achieve for number 6. So absolutely good problem there. One more for this video, number 7 here, and then we'll do the rest in another. In number 7, I was looking at this problem where I had the integral of dx over x cubed minus 15x squared plus 48x plus 64. Now, what I did on that one is that problem is not going to factor nicely. You could try factoring by grouping and stuff like that. It's not going to be pretty. So I took the easy way out. I went ahead and I put this function into my graphing calculator, and I noticed it crossed the x-axis one time at x equals -1, and it touched at +8. So what you're supposed to remember is, oh, anytime it touches, it means it's a double root. I knew since it touched at +8, I had the factor x minus 8 squared. And since it crossed at -1, I knew I had the factor x plus 1 to the first. So I just immediately used my calculator's graphing capabilities to easily factor this. So then I can say, well, then my original problem factors to be 1 over x plus 1 times x minus 8 quantity squared. Now, I need to reduce that to its simpler partial fractions to make the integration possible. So I said a over x plus 1 plus b over x minus 8 to the first plus c over x minus 8 to the second. Now, multiply by that least common denominator on both sides. The left-hand side, of course, you have the numerator of 1. On the right, the a is going to be multiplied by just the factor x minus 8 squared. The b, one of the factors of x minus 8 are going to cancel, but you're still going to have x plus 1 times x minus 8. And the c, you're going to cancel out both factors of the x minus 8, and it'll only be multiplied by x plus 1. And so now, if you're trying to solve for a, you can say, well, let's let x equal -1. We know that that's going to solve for a because it would make the term in its denominator 0. So I can say, all right, if I let x equal -1, on the left-hand side, still 1. It doesn't have an x to plug in. The right-hand side, b would be multiplied by 0, c would be multiplied by 0. A is multiplied by -1 minus 8, -9 squared. -9 squared is 81. 81a is 1, so you get a is 1 over 81. Now, when you plug in an x equals 8, it should enable you to solve for c. So when I do that, again, the left-hand side is still 1. The right-hand side, you would have a times 0, and you would have b times 0. The c is going to be multiplied by 8 plus 1, 9. I get 9c is 1, thus c is 1 over 9. Now, I have my answer for a and c. Yet again, you need to be a little more clever to think for how to solve for b. Well, I noticed that a was a coefficient of x squared, b was a coefficient of x squared, and that there is no x squared term on the left-hand side. So I can say, well, the coefficient of x squared is supposed to be 0. The coefficients of x squared on the right are a plus b. So this just tells me that b has to be the negative of a, thus b is -1 over 81. So now I go back into my integral and I can say, well, then this original integral is equal to a 1 over 81 times the integral of 1 over x plus 1. And then again, I want to bring the b out in front and say minus 1 over 81 times the integral of 1 over x minus 8 with respect to x. And again, I'll bring the c out in front and say plus 1 over 9 times the integral. Now that the c is out in front, your numerator would be 1, your denominator would be x minus 8 squared. I went ahead and called that x minus 8, and I meant to put to the -2 power there. And then you say, and I integrated it correctly over here as if it were the -2 power. So then you can say, well, then this term right here, you know that's going to become x minus 8 to the -1 over -1. That -1 is just going to change the sign on this term and make it minus 1 over 9. And then the x minus 8 to the -1 becomes x minus 8 to the +1 in the denominator. I also here, I kind of liked condensing these down. Since both of these had coefficients of 1 over 81, I went ahead and condensed them to one logarithm and said, well, this would be 1 over 81 natural log of x plus 1. This is the same thing, except it's minus 1 over 81 natural log of the absolute value of x minus 8. So I just said, well, the only thing that negative would be when I condense is that I would divide. So I called this 1 over 81 natural log of x plus 1 over x minus 8, all inside the absolute value. And then minus our 1 over 9 times x minus 8 to the -1, which means x minus 8 in the denominator, plus your constant of integration. It's a gorgeous problem there. Now, you'll notice my answer for number 12, I entered it just like that. Now, sometimes Achieve doesn't like the condensed answers. It accepted it just fine in this problem, as it should have. I think the condensed answer is superior to the non-condensed version, but I'm sure if you put the non-condensed answer there too, it would be fine in this case. All right, guys, you can look for another video with the remaining problems in this section, including the absolutely wonderful number 11.